of PKC 2023. So we have 3 talks in the session. The first one is unidirectional updatable encryption and proxy re-encryption from DTH. So it's a joint work by Pihen Miao, Sikar Patranambis, and Gavin Watson, and Gavin will present the talk.
Okay, thanks for the introduction. I guess you can all hear me. Yeah, so it's a joint work with Pihen and Sikar. So I guess first of 2 talks on updatable encryption. So what's kind of the motivation for looking at PRE and updatable encryption? Well, we know that kind of building crypto systems is hard, but also deploying them is kind of hard. You need to be very careful with many things, such as key management. One of the kind of best practices with key management in many use cases is that periodically you want to rotate your keys. This is mandated in standards such as PCI DSS, where from time to time, kind of for your backups, you should be rotating the keys and then kind of re-encrypting all your ciphertexts so that they're kind of in line with the most recent key. But doing this kind of rotation and decryption and encryption of these ciphertexts is kind of a bit of a pain. So what are the kind of advanced primitives that can help us in this setting? Well, there are 2. One is proxy re-encryption, and the other is updatable encryption. So what is proxy re-encryption? Well, this is a public key notion, and that allows you to delegate kind of decryption ability to someone else. First proposed in, say, the early 90s. So say Alice is going to go away on a vacation, and she needs someone to look at her encrypted email while she's on vacation. Yeah, so a proxy re-encryption scheme would allow her to generate some re-encryption key, which she can give to a proxy, and then the proxy can use that to re-encrypt all her encrypted emails, so they can now be decrypted by Bob. But the proxy would learn nothing about the plaintext when it does this re-encryption. So on the other side of this, what's updatable encryption? Well, it's a symmetric key notion. Again, it's going to allow you to update ciphertext without revealing the plaintext, but it's more suited for situations like outsourced storage. Yeah, so I encrypt all my data, I outsource it to the cloud where it's going to be stored. I don't want to have to kind of download that, decrypt it, encrypt it again, and upload it again to the cloud, because that's kind of a big kind of cost on communication and time. So instead, I can generate a little update token. So it's a small token, and then I can give that up to the server. It can move kind of ciphertext encrypted in epoch E now to ciphertext encrypted under the key for the next epoch, again, without revealing anything about the plaintext associated to these ciphertexts. Okay, so a little bit more then about the syntax of these schemes. So as I mentioned, proxy re-encryption is a public key scheme. So it has kind of the basic key gen, encryption, and decryption. Then you have 2 additional algorithms, which are a rekey generation algorithm, which takes kind of key information about the source keys and the destination keys and allows you to generate a re-encryption key. And then a re-encryption algorithm, which would take that re-encryption key in a ciphertext and then transform kind of to a new ciphertext, which is encrypted under the destination key. Similarly, for the symmetric key setting with updatable encryption, you have your key gen, your encryption, and your decryption. And you again have these 2 kind of similar types of algorithms. One's a next algorithm, which takes the key for the kind of old epoch and will generate the key for the new epoch, and an update token, which would allow you to do these transformations. And then an update algorithm, which takes that kind of update token and ciphertexts and will transform to the ciphertext for the new epoch. Okay, so these are kind of the basics of these schemes, but these schemes come in many different flavors. And that a lot of that relates to kind of the directionality of kind of what direction you can do these re-encryptions in, and what you can get from the different keys. So there's kind of 2 flavors in terms of bidirectionality and unidirectionality. And this kind of corresponds to both the ciphertext and the key updates. But in essence, for the ciphertext updates, kind of a re-encryption key would allow you to go either in one direction or the other direction, whereas a unidirectional kind of scheme, only the re-encryption key can be used to go in one direction. In the PRE setting, kind of the big difference for your keys comes in that when you're generating your re-encryption key in the bidirectional setting, you need to use both the source secret key and the destination secret key. Whilst in the unidirectional setting, you only take the source secret key and the destination public key to generate your kind of re-encryption keys. In UE, when it comes to key updates, there's even more variations. So again, you can have your ciphertext updates, which are bidirectional, unidirectional, but then in key updates, they can be bidirectional. So like given an update token and a key from one epoch, then you can derive the key for the opposite epoch. So for E to E+1 or E+1 to E. But then kind of we have different then flavors of unidirectional. So there's forward leak, that given an update token and the key of the old epoch, you can derive the key of the new epoch, but you wouldn't be able to derive the key in the opposite direction. Or the inverse of that, where the backwards leak, where given the update token and the key of the new epoch, you can derive the key of the old epoch, but you can't do it the other direction. Or there's no leak, no direction key updates, where given an update token and a key, you would not be able to derive the opposite key in either direction. So what we're actually going to, like, the nicest thing you would think to build a construction in the no directional setting where you don't have any of this leakage, but that's kind of maybe a bit hard. So we can actually concentrate on the backwards leak setting and define a scheme here. And you'll see in the next talk, Jaejin will talk about how these are actually equivalent. And the intuition between that is because, say I have the update token and the key of the new epoch. So if I was in the backward leak setting, I can use that to derive a key from the old setting and decrypt my ciphertext there. But if I wasn't in the backward leak setting and I couldn't do that, well, I can just take the update token, move to the new epoch, and then using the new key, I can do the decryption anyway. Okay, so for the rest of this talk, I'm going to be looking at how we construct unidirectional schemes, and in the UE setting, we'll be kind of constructing a scheme which is in this backwards leak setting. But building unidirectional schemes is hard. So we saw kind of the Test of Time award earlier this week was awarded to a scheme which constructed a unidirectional PRE, which was CCA secure. One of the things about that scheme is that actually it would only support one re-encryption for each ciphertext. And extending to get unidirectional schemes which permit multi kind of re-encryptions is quite difficult. So it requires kind of much stronger kind of building blocks or assumptions. And it's similar for UE. If you want a unidirectional scheme with multi-hops, then you need to use some kind of heavy tools. So what we want to try and do is, well, can we do something which is a bit simpler? Can we build either UE or PRE unidirectional schemes that are multi-hop from DDH? So I'll concentrate now for the rest of the talk on kind of the intuition behind our updatable encryption schemes. So let's talk a little bit about security notions for updatable encryption. So in any security notion, we define a security game. An adversary is given access to different oracles. So as you would expect, they get access to an encryption oracle where they encrypt messages. They can get access to a next oracle, which allows to move things to the next epoch. So then when you move to the next epoch, the encryption oracle is now using the key of the new epoch. You have an update oracle, which allows you to update ciphertext to the current epoch, with some extra restrictions on it, which has to be that the ciphertext that are submitted are previously honestly generated. You have a corrupt oracle, which allows you to obtain either a secret key or an update token from a previous epoch. And then with all these, you then have some challenge which you need to satisfy. So there's a few different notions which you can have in the UE setting. The first was kind of like the CPA notion, which is called IND-enc. Just as you expect, the adversary submits two messages, M0, M1. It receives a ciphertext and needs to say whether it received the encryption of the M0 or M1. We then have a post-compromise notion, which is to help kind of show that you can't kind of link ciphertexts across epochs. So there, the adversary would submit two ciphertexts, C0, C1, and it has to distinguish whether it received the re-encryption of C0 or the re-encryption of C1. And then finally, you can have a combined notion, which has these two notions together, where the adversary submits a message and a ciphertext, and they have to distinguish whether they received a fresh encryption of M or a re-encryption of C. Okay, so let's first kind of talk about building an IND-enc secure scheme. So what's our first attempt? Well, consider the following kind of solution. So take any kind of symmetric encryption scheme. We'll take our ciphertext, which we encrypt in epoch E, just to be the encryption of M. in this scheme. And we'll have our update token to get to the next epoch is going to be the old epoch key encrypted under the new epoch key. Then when we do our update operation, we're just going to append this token onto our ciphertext. And then if we wanted to decrypt in epoch E+1, well, we know the key KE+1. We use that to unwrap and get KE, and then use that to then decrypt our message. And then obviously we wanted to move to the next epoch. Well, the next update token would be key E+1 encrypted under key E+2. So our update operation would just be appending that, and so on and so on. So we're just kind of appending on these update tokens each time. Problem with this is, like, it's very kind of trivial to attack this. We can just use a corrupt operation, get an encryption key from a previous epoch, and then use that to attack our challenge ciphertext. The issue here is there's like no randomization, there's memory of these keys across all epochs and across all ciphertexts. Yeah, all ciphertexts are sharing the same keys, and we can always go back and decrypt something further back in the ciphertext with these keys. Okay, so it's clear we need to add some kind of extra randomization here. So consider a new building block. So this we call key and plaintext homomorphic encryption. So this is a public key scheme, which again, keygen, encryption, and decryption. But then we have an additional operation which we call eval. So eval takes as input the public key and the ciphertext, and then it has two linear transformations or permutations, which the first one will act on the key space. So it'll transform your public key to a new public key and your ciphertext to something encrypted under a key related to the old key transformed based on this permutation. And then we have a second final input, which is some other transformation on the message space, which will then transform what the ciphertext was encrypting. So this is a generalization of the circular secure encryption scheme introduced by Boneh et al. In 2008. And crucially, you can show that you can construct this with, of course, restrictions on the distribution of your keys and these permutations from DDH. Okay. So now using this building block and the kind of similar idea we had from our first construction, can we use this to construct a unidirectional UE? So now we're going to use the KPHE as our building block. So the secret key of our epoch is just the key pair for this encryption scheme. Our ciphertext is going to be the encryption of the message under the public key of your KPHE scheme. And then your update token is going to be the secret key of the old epoch encrypted under the public key for the next epoch. Now, when we do our update operation, we pick some random permutation pi, and then we're going to do a transformation on each the ciphertext and on the update token. So first of all, on the ciphertext, we do a transformation on the key space. So now this PKE becomes PKE prime, and we get a new ciphertext now under this new kind of random key that we've just transformed to. And then and we don't do any transformation on the message space. We just do the kind of identity transformation. On the update token, we now do a transformation where we don't do any transformation on the key space. We just keep that as kind of the identity. And we do a transformation on the message space. But as our message was the secret key SKE, and we're doing the same transformation here, we're now getting an encryption of SKE prime. So then later, when we come to decrypt in epoch E+1, say, we know kind of the secret key for E+1, we decrypt, we get this SK prime, which is now kind of the one associated to this first part of our ciphertext. And so we can decrypt and recover the message M. And so we can if we wanted to update to later epochs, it's the same thing. Now our update token is the encryption of the old epoch, and again, under the next epoch, we pick a new random permutation. We do a transformation on the last element of the ciphertext to change its key space. And then we transform the update token to move the message space and then append that on. Okay, so now it avoids the issue of the previous scheme. There's no memory of prior epochs because we're transforming the keys into new random keys. And there's no keys shared across any ciphertext because we have a different random permutation for every update operation. Okay, great. So this scheme, you can prove achieves the end-ink notion, this kind of CPA notion of updatable encryption. You can extend this scheme to also satisfy the end-up and the end-UE schemes by just hiding the number of re-encryptions that have been performed. So just making sure that ciphertexts are the same length within an epoch. So all ciphertext and epoch must be of the same length. And then also some additional kind of re-randomization operations just to make sure there's nothing you can use to link across epochs. Similarly, you can use a similar approach to then also construct unidirectional proxy re-encryption schemes. The complication maybe just comes a little bit more in the security analysis, and that relates to your re-encryption graph. So in UE, all you're doing is re-encrypting from one epoch to the next. So your re-encryption graph is just a chain of ciphertext. Whereas in PRE, you can re-encrypt to like any party or participant in the kind of universe. So what that means is that you can get some cycles in the re-encryption graph. So the security analysis has to kind of use some of the circular encryption properties of the KPHE scheme to be able to prove the CPA security. Okay. So one complaint you might have about our approach is that you have a linear growth in the re-encryption. So every time you do a re-encryption, you add an additional ciphertext element. So everything is growing with each re-encryption. So if we look at it from a theory perspective, okay, we might not be happy with this, it might do better, but actually we've done something good, is we've been able to construct some a unidirectional UE and a multi-hop PRE scheme from DDH, which is like wasn't known until we were able to do this. Also on the practical side, well, maybe you can look at it like, in reality, we probably don't want to do an unlimited number of re-encryptions. And how often do we do re-encryption? So if you think about the outsourced storage use case, well, probably we only want to re-encrypt things once a year, and we only care about ciphertext kind of living for 10 years, say. So in the lifetime, we only need to do kind of 10 re-encryptions. So maybe that might be okay in practical settings, that like the size is only going to go up to these kind of 10 ciphertext elements. But it would be nice to kind of construct PRE scheme or PRE and UE schemes from DDH which don't have this linear growth, either kind of in our case in the size of the ciphertext, or I think in the next talk in the size of the keys that are used. So that remains an open problem. With that, I thank you for listening. That's our full papers there. I'm happy to take questions.
Okay, so there's an answer at any point.
Thanks for the talk. My question is there any generic transform from UE to PRE or from PRE to UE?
So you can, obviously the difference being the public key and the symmetric key setting. So it's easy to go from PRE to UE. Going the other direction, obviously you have the difference in that you want to move to public key, but also you need to support these different re-encryption graphs. And so that's where you have some challenges.
Yeah, so no generic transform exists now. Yeah.
I mean, so I could construct a UE scheme from PRE.
Yes.
But going the other direction is harder.
Okay, thank you.
Thanks.
Any other question? Okay, so let's thank the speaker again. Okay, so the next talk is backward link unidirectional updatable encryption from homomorphic public key encryption, which is a joint work by Yojong Gotland and Yaxin Pan, and Yaxin will present the talk.
Thank you for the introduction. So Thanks for coming to my talk. So yes, we will talk about this updatable encryptions. This work about updatable encryptions. This is a joint work with our former postdoc, Yao Jiang Gaoziland. So let's jump straight to the conclusions. So in this paper, we basically have two main contributions. So the first one is we prove equivalent results that shows that the backward leak unidirectional key update is equivalent to the no directional one. And the second main construction is two generic constructions about updatable encryptions. So the first generic constructions is based on homomorphic public key encryptions. So this is like a concurrent work with the first talk. I think we follow slightly similar idea, but there's also some differences. And the second generic constructions we constructed from a bootstrapable public key encryption scheme. So let's start. So in my talk, instead of telling you all the detailed proof and so on, I will try to be giving you a more overview, a more informal way of our work. So let me recall the updatable encryption scheme again. So once again, this is a symmetric key primitive, but it uses public key primitive to construct this. So that's why we are here. So in the updatable encryption, so a user usually will rotate its key from K0 to K1, and then there's some update tokens. And the user can send the update token to the cloud, for example, to update the ciphertext to a new ciphertext that can be decrypted using K1 of the same message. And the client only needs to store one key. It just needs to store the fresh key. And informally, the security basically saying that giving out all the public informations, the confidentiality should preserve. Like if you give out the ciphertext, give out the tokens, it should not leak anything about the plain text. So in our work, we only focus on confidentiality. So how to capture this a bit formal is that we consider this epoch model. Let's consider like this is the timeline, right? So this is 1, 2, 3. This is the time, and this delta it means for the update tokens, and K is the key, and C is the corresponding ciphertext of the same message. There's different like directions updates. Like for example, the bidirections means that the adversary can, right? If the adversary get the old key and also the new token, the adversary can infer the new secret key, right? And that's usually called the forward directions. And the backward direction means if the adversary get the update token and the new key, it can infer the old secret key. So the bidirection means both direction is possible. And also there's this direction is also defined with respect to the ciphertext updates. Right? You can also use this token to shift the ciphertext in the forward directions or in the backward directions. And for unidirections, for the early work, they consider only the forward directions, this forward leak unidirectional updates. It means that the adversary with the token, it can only go the forward directions, but not the backward direction. And for unidirection ciphertext updates, it's always forward. So we only consider the forward directions. And for backward leaks, so it's proposed by Nishimaki last year at PKC. It basically says that the update token can only help you to go in the backward directions, but not in the forward directions for the adversary. And again, the ciphertext updates is always forward. So the no direction is that you cannot go either way, basically. So personally, I think the backward leak is more reasonable because it means that the ciphertext always going forwards, but your key can only go in the backward. So there's a few observations that you can make. The first observation is that it seems to us that the unidirections it leaks less information compared to the bidirectional ones, right? So then maybe you will ask the questions, is it the unidirections, they are more secure? And the second observation you can make is that it seems the UE without any direction, with no direction key updates, leaks the least informations. Maybe the no direction setting is the most secure. But the reality seems to be a little bit counterintuitive. Actually, there is a discussions about whether the directions matter or not. Right? So first of all, like my co-author, like she published a paper that says that, the direction doesn't matter that much, but then 2 years afterward, there's another paper saying that, okay, the direction actually does matter, right? It seems to be very confusing. And maybe you will even think maybe there's one of them is wrong, there's contradictions. So I think usually like in this place, people should go into details because, the detail will answer you this question, I think. So let's take a closer look at these two results. So here in the setting, I consider only confidentiality and only consider this forward direction ciphertext update. Okay. Then we can draw this graph. There's no direction here, right? Basically, the work from Encryption 20, it shows that the no directions imply bidirections, right? But not the other way around. And also, it's also show the bidirections is equivalent to the forward leak key update. Okay, that's what the first work show. The second work actually show that starting from the bidirectional, you cannot imply backward leak key update. But now it remains open is that what is this relations? We don't know it. And also what is the relation here, right? I mean, if we are clear about the relation between the no directions and the backward leak directions, then we sort of imply here. So the result we actually have is that we show these two notions, they are equivalent. And based on that, it means that the backward leak can imply the forward leak, but not the other way around, because you can go this way to imply that, but this way you cannot go because of this one does not imply. Okay, and also this one. So that's the whole picture. After our work, we sort of complete the whole picture. So let me give you a little bit about this security notions. And actually, when you define this formally, it needs to involve this game. Basically, this is you can think about this as IND-CCA or IND-CPA for symmetric encryption. So you have the encryption oracle, you have the decryption oracle as usual, and you can move the epoch in the form. I mean, you can update the epoch as time going, and you can corrupt either the key or you can corrupt the update tokens. And you can update the ciphertext, for instance, and so on. And in the end, the adversary will output a message and a ciphertext of it under some epoch. And then the simulator or the challenger, it will either encrypt a fresh ciphertext or it will just update the ciphertext. And then the adversary need to distinguish whether the ciphertext is a fresh ciphertext or is an update ciphertext. So so what makes it difference between like backward leak UE or no directional UE is this trivial wins conditions. So it defines a set of trivial wins conditions. So to show that two notions are equivalent, basically we need to show that like these two set of trivial wins events, they imply each other. They are equivalent to each other. Okay, that's the main idea. So in our paper, we will do a detailed analysis of it. So I'm not going to show it here. So now let's jump to the second contributions, which is the two generic constructions that we have proposed. So let me zoom out a little bit to have like a bigger picture of what we have right now. So what kind of constructions that we have is that if we consider the backward leak, there's only one construction. It's from LWE. Okay. from Nishima key. And if you consider no directional, so we only have constructions from IO. So this is before our work, before our equivalent result between the backward leak and no direction. And also, if you consider bidirectional, there's the DDH constructions, there's DDH and random oracle and so on. So you can see that all these constructions, they're constructed based on a concrete assumptions. So the question we want to ask is that, is there any generic constructions of updatable encryptions? Or is there any updatable encryption from other assumptions outside of here? So we are interested in proposing updatable encryption generically. The first generic construction we have is we base on this key and message homomorphic public key encryptions. So here you can think about algama actually. So basically, key homomorphic means you can homomorphic, like the keys are homomorphic. I mean, it means that the distribution of the homomorphic keys are indistinguishable from the real key. I mean, you can generate new key from an old key homomorphically. Okay. And you know, now you already get a little bit of flavor about how our scheme is, because we really need this homomorphic property to have our key updates and so on, and ciphertext update, for instance. So, and we also need an additional property is called message homomorphic. So it means if you fix a public key, you have two ciphertexts of two different messages, you can homomorphically to add them together, basically. Think about algama, right? This is the example of it. And actually, you can also have regex that also satisfy these properties. So which means from our first generic construction, we have two instantiation, one based on DDH, one based on LWE. So this is the scheme. You can find it in our paper. So, I mean, don't look at it. So, I mean, basically just, you know, this homomorphic property can help you to update the key and also update the ciphertext. That's basically it says here. So that's the first constructions. And the second constructions, we need this notion called bootstrappable public key encryptions. This is a notion from Gentry's homomorphic fully FHE. Basically, it says that for a public key encryption scheme, if there exists a re-encryption algorithm such that for all like public key, you have two pairs of public key and secret key, right? So this re-encryption can have this interesting properties that if you put in the encryptions of the SK1 under PK2 here, right? And this D is the decryption circuits of the same scheme. If you put this here, you re-encrypt it, it will give you the encryptions of public key 2 under the message M, okay? And this C is encryptions of the same message, but under public key 1. You sort of, after you re-encrypt it, you just shift the public key, right? And this re-encryption essentially is for updating the ciphertext, basically, right? So you can see, I mean, this scheme is much cleaner. So this is like the public key and it's the same as the public key encryption scheme, but so when you do the key update, you encrypt the secret key, and then when you update, you re-encrypt it. Because of this bootstrappable property, you can update your ciphertext, basically. And that's the big picture of our paper. So let me remind you once again, we have two results. The first result is equivalency. We show the equivalence. So under the ciphertext update is forward leak. Then the backward leak of the key update is equivalent to the no directional key updates. And we also have two generic constructions for backward leak updatable encryptions. And because of this equivalent result, this also, like these schemes are also no directional. Okay, and that's all for my talk. And sorry, so there's the same open problems that can you do updatable encryption more efficient with less, with shorter ciphertext or with shorter keys. That's an open problem. And that concludes my talk. Thanks.
Okay, so thanks to the speaker. So any questions?
Hi, thanks for the talk.
Thanks.
So I have two quick questions. So the first is the construction from bootstrappable PK for the no directional scheme? Or
For the backward leak. But I mean they are equivalents. So.
Because in the table I saw that the only construction from the no directional scheme is from IO, right?
Yes, yes. Yes, you're right. Yeah.
So how does the bootstrappable PK compare to IO?
I think that one you can construct it from LWE.
Okay.
So
And the second question is that do you think that bootstrappable PK can be useful in constructing KDM secure encryption?
I'm not sure about this. My feeling is yes. I'm not sure, but yeah.
Okay. Thanks.
Thanks.
Any other questions? Okay, so maybe I will ask a question.
Yeah.
So you said that the only known backward leak unidirectional updatable encryption that is known is due to Nishimaki, which is based on LWE. And you're like, we also know that kind of fully homomorphic encryption from LWE. So one thing I am curious is that like, if you instantiate this your homomorphic public encryption from LWE and then apply your generic technique, is it that essentially you will end up getting Nishimaki's construction, or you will get something different?
It is something different. It's something different that I know. Yeah, but we have two LWE constructions because like both generic can go to the same goals. So I think the second is a bit less efficient. The one with bootstrappable public key is less efficient. So the first one maybe we get something similar to the Nishimaki. Yeah.
I see.
Yeah.
Thanks a lot. Okay, so let's thank the speaker again. Okay, so the last talk of the session is functional encryption against probabilistic queries, definition, construction, and applications. So the authors could not make it to the talk. So Yang Liu will present the talk on their behalf.
Okay, thank you. Hello, I'm Xiangyu Liu, and I'm here to deliver the talk, Functional Encryption Against Probabilistic Queries, Definition, Construction, and Applications. And the authors are Geng Wang, Shifeng Sun, Zhedong Wang, and Dawu Gu from Shanghai Jiao Tong University. Okay, we may start from functional encryption, FE. FE was first introduced by Bourne et al. In 2011, which can calculate the function output FM given the encrypt message ink M, and there's nothing else about the message M. Function encryption scheme consists of 4 algorithms. Despite the normally defined algorithms, setup, ink, DAC, as in public key encryption, there's another algorithm, KGene, in functional encryption, which takes the master secret key as and a function F as input and outputs a functional key, SKF. Well, in the decryption algorithm, function key SKF instead of the master secret key MSK is used, and the function value FM instead of the message M itself is returned. Function encryption is an important method for computing encrypted data, especially for cloud computing, as the cloud server can take ciphertext as input and output the required computation result as plain text, which is different from homomorphic encryption. FE4P/poly can also be used to construct indistinguishability obfuscation. Well, the standard IND security is equivalent to the natural notion of semantic security in public key encryption. Well, we first formally recall the definition of IND security for FE. Well, as shown in these slides, the adversary A cannot distinguish between a ciphertext from M0 and a ciphertext from M1, even if it's allowed to query secret keys SKF for any polynomial times for many different function F, providing that FM0 equals FM1. We say that A is admissible if it only makes queries such that FM0 equals FM1. And the simulation-based security definition for FE is first formalized in BSW 11. And the real game is defined similar as in the IND game, but the adversary submits only one message M and outputs alpha, which can be any help information to distinguishing between the real game and the ideal game. Well, in the ideal game, the adversary interacts with a simulator S, which may answer any query arbitrarily, but only given the functional value of M, not the message M in play. And the SIM security requires that the real game and the ideal game are computationally indistinguishable, and is known to be stronger than the IND-based security model. There are limitations in both IND-based and SIM-based security definitions. Well, first in BSW 11, it was shown that SIM secure FE for P/poly cannot be constructed for unbounded ciphertext queries before a single key query. And note that in SIM-based definition, many CT security cannot be reduced to one CT security. And in AGVW 13, it was shown that SIM secure FE for P/poly cannot be constructed for unbounded key queries before a single ciphertext query. These impossible results hold even under the random oracle model. And second, for IND security, the adversary is only allowed to query on F such that FM0 equals FM1. If F is a one-way permutation, then the adversary is not allowed to make any single queries. And thus, the security definition for FE degenerates into that of PKE, which means that any single function key lacks the message M. However, for an intuitively secure FE, it should only lack FM, which cannot be used to recover M. So actually, we need for a new security definition. And we wish that a good security definition for FE should satisfy the following requirements. First, the new security notion must avoid the counterintuitive example in the literature. And second, there must be a construction of FE for P/poly under the new security notion that supports both unbounded ciphertext and key queries. And third, any SIM secure FE scheme should satisfy the new security notion so that we are able to discuss the bounded ciphertext key security for existing SIM secure schemes. And last, the new security notion should be stronger than IND security so that the properties for IND security also hold for even this new security notion. Now, an obviously method for solving the counter example for IND security is to lose the restriction on the adversary such that it's still allowed to make query on F, even if F is a one-way permutation. Well, we may start from the distributional indistinguishable security in AM18 by letting the inputs of ciphertext queries be a pair of message distributions instead of a pair of messages. However, if F is a trapdoor function, that is public key encryption, then FM0 and FM1 can be computationally indistinguishable. while the adversary A holds the trapdoor can easily distinguish between M0 and M1. This means that DI security cannot be satisfied for trapdoor functions unless we suppose that the distinguisher can acquire the trapdoor by default, which contradicts with the normal notion for computational indistinguishability. Well, we solve this problem by presenting a stronger notion for computational indistinguishability called strict computational indistinguishability. Well, as shown in these slides, in the definition, let D be a PPT algorithm that outputs a pair of distinguished D0 and D1. We say that the distinguished from D are strictly computationally indistinguishable if there is no auxiliary string X corresponding with D0 and D1 such that D0 args and D1 args are computational distinguishable. Well, that's the formal definition of strict computational indistinguishability. And in the definition above, the auxiliary string args can be viewed as the trapdoor in distinguished D0 and D1. This additional auxiliary string has no effect on function families without trapdoors. Just consider PKE for a pair of keys, PK, SK, generated from key generation algorithm. SK can be the auxiliary string if PK is fixed. But if we choose random PK, then there's no such args as long as PKE has semantic security. So our definition of IND-based security is also from a IND-CPA game between the adversary and the challenger. The game is almost the same as the IND-CPA secure game, except that we allow probabilistic queries in both key queries and ciphertext queries, and the admissible condition queries the strict computational indistinguishability between M0 and M1. This slide shows the theory that if FE is a SIM secure functional encryption scheme, then FE is also P&D secure. That means SIM secure is stronger than P&D security. And that's the proof sketch. The second theory says that if FE is a P&D secure functional encryption scheme, then FE is also IND secure. And the proof is rather simple. Any adversary in IND secure game is also adversary in P&D secure game. The results thus follows. And we have the following theory. If FE is a one CT P&D secure functional encryption scheme, then FE is also many CT P&D secure. And as for the proof, we just use the standard hybrid argument. And from the theory above, we see that P&D secure does not suffer from the BSW 11 impossible results. And what remains is the existence of adaptive P&D secure FE scheme for P/poly, which supports unbounded key, so that our new security definition can avoid AGVW 13 impossible results. We use the ABSV15 generic transformation, which can be extended into P&D security that we can construct an adaptive P&D secure FE scheme for P/poly from a selective IND secure FE for P/poly, while given an adaptive IND secure one CT private key FE for P/poly, a symmetric encryption scheme, and a pseudorandom function family. Now we only need to prove the existence of adaptive P&D secure one CT private key FE. And similar to ABSV15, to prove the existence of IND secure private key FE with one CT and unbounded key queries, we rely on several results in the literature as well as in this paper. First, in GVW12, the authors constructed a one-key unbounded CT SIM secure private key FE scheme from for P/poly, which is also one key unbounded CTP and secure private key FE scheme. And in BS15, the authors gave the generic transformation from private key FE to functional private key FE. And we extend it into PMD settings. Then we can swap keygen and inc in a function private key FE with one key and unbounded CT to obtain a private key FE with unbounded key E and one CT. Next, we show how to construct PND secure functional private FE. The construction relies on the following primitives: SKFE, pseudorandom symmetric encryption scheme, and a pseudorandom function family. And the detailed construction is shown as follows in this slide. And the idea of this construction is similar to the one in BS15, but more complicated since we consider probabilistic queries. The BS15 construction used two symmetric keys, K prime, to hide the two functions F0 and F1, correspondingly in both the message private and functional private game. However, in our P and D secure settings, in message private games, adversary lengths an extra function F, while in function private games, adversary lengths only two distributions, F0 and F1. So we need three symmetric keys to encrypt F, F0, and F1 correspondingly, and an additional game to switch between them, while the other parts of the proof is similar to that in BS15. Next, we introduce a specific application scenario which can be constructed from P and D secure FE. This application is inspired by the counter example for IND-based secure FE for one-way function. We show that how we can use P and D secure FE to output the hash of a secret value. Concretely, we can turn any hash function into a blind hash, which can be used to hash a ciphertext instead of the message in plain. Like blind signature, we name this new primitive blind hash. We require the one-wayness of a blind hash system. That is, given the blinded hash function and the ciphertext, we cannot recover the message. And this slide shows the construction of blind hash system in detail. And the one-wayness of the construction above requires P and D secure FE, since IND secure FE cannot handle one-way hash functions. We may skip these slides. Now, we give another application scenario which can be constructed from P and D secure FE. In the paper DN21, the authors introduced a universally proxy re-encryption and gave their construction from probabilistic I/O, where both the delegator and the delegatee can be arbitrarily PKE schemes. Here we discuss a weaker version of universal PRF, where only the delegatee ciphertext can be encrypted by arbitrary PKE schemes. And we call it semi-universal PRE. A semi-universal PRE can re-encrypt a ciphertext into ciphertext for any PKE schemes, such as RSA, ECC, lattice-based schemes, and so on, and decrypt correctly into the message. And this slide shows the detailed construction of semi-universal PRE. The IND CTA of the construction above requires P IND secure FE, since IND secure FE cannot handle public key encryption. And we also know that the construction above cannot use DI secure FE or IND secure randomized FE. Well, to make conclusion, in this work, we proposed new security definition for FE between SIEM and IND, namely P-IND security. And we proposed the construction of P-IND secure FE for P/Poly supporting unbounded ciphertext and key queries. And we also showed applications from P-IND secure FE. They are blind hash system and semi-universal proxy encryptions. Well, as for further works, there are three directions. First is to design direct construction for P-IND secure FE. And second is to design more applications, to explore more applications from P-IND secure FE. And the third is how to use P-IND secure FE to simplify the construction of I/O. Okay, so that's the main idea of this talk. And since I'm not the original author, so if you have any question, just send the email to Gengwang, the original author. Okay, this slide shows the email address. Thank you.
Okay, any questions? Okay, so just a quick question. So
I will try my best to answer the question.
Okay, so yeah,
I
just curious, like, is the notion that you define? So you said that one motivation is to just sidestep the impossibility result.
Yeah.
So do like how strong you think? Like, do you think this notion is kind of the optimal that sidesteps this impossibility, or like? Do you have any comment? Just your view.
Let me see. I will try my best. Actually, in my mind, the motivation of this work is to circumvent the impossible results for the SIEM-based security. So during this process, the authors they found we can use probabilistic distribution to solve this problem, but there are some details we need to discuss. So that's the motivation for we design a new security notion between SIEM-based security and IND-based security. Okay, so that's my understanding.
I see. Okay, so let's thank the speaker and all the speakers of the session.
Thank you.